Let's see how Einstein derived Lorentz transformations in his famous paper from 1905, which is called On the Electrodynamics of Moving Bodies. In particular, we will consider, just like he did, a stationary, quote-unquote stationary system capital K, like this, with coordinates t for time, x, y, and z. And then we will also consider a moving system, lowercase k, and the coordinates will be tau, this is the time coordinate, then we have xi, eta, and zeta, where tau and t, as I said, are the time coordinates. Tau is the time measured in this frame lowercase k, whereas t is the time measured in this frame called the stationary frame capital K. And the axis xi will be parallel to x, eta will be parallel to y, and the axis z will be parallel to zeta. Now, k, lowercase k, is the moving system. It is moving with respect to capital K, and the motion is along the axis xi, or x, because xi is parallel to x, and at the initial time we suppose that the origin of the two systems coincide. Now, the motion, as I said, is only along xi. So the axes, all the axes will remain parallel, as we can imagine. And from the system lowercase k, we emit a light ray from the origin at time, let's call it tau 0, which is measured from the moving system along the x-axis. So this light ray is emitted along the x-axis until we reach a point with coordinate x prime, and at the time tau 1, the ray is reflected back. So we are moving in this direction. The light ray, of course, propagates with the velocity, with the speed of light, c, in every frame of reference. Then, when we reach a point with coordinate x prime, the ray is reflected back and it will go back to the origin, and the time taken for this light ray to be reflected back to the origin is tau 2. Now, we define x prime in particular to be x minus v times t. And if we define it like this, x prime, y, and z, which are measured according to the stationary axis, they will not depend on time according to the system lowercase k. Then, from simultaneity, we must have this relation tau 2 minus tau 1 equal to tau 1 minus tau 0. Or, from this, we get tau 1 equal to 1/2 tau 0 plus tau 2. Or, by considering the function tau as a function of x prime, y, z, and t, we have tau of x prime 0, 0, t plus x prime divided by c minus v. And this is simply due to the fact that this is tau 1. So at tau 1, the first coordinate here is x prime, then these two coordinates will remain equal to 0, and then here in the time coordinate we have t plus this value, which is x prime over c minus v. And in particular, we have to think about this. Why does that appear? Here in the denominator we have c minus v, which is the velocity of the light ray with respect to the origin of the system uppercase K after the light ray is emitted. So after the light ray is emitted, since the two frames are moving away from each other, this distance is increasing, this distance here between the two systems. And therefore, the velocity of the light ray with respect to the origin, as seen from the stationary system, is c minus v. And then we have 1/2. Here we have tau of 0, 0, 0 t. This represents simply tau 0. Then we have plus tau of 0, 0, 0 t plus. In this case, we have the same contribution x prime over c minus v, but we also have another contribution, which is x prime over c plus v. And in this case, this contribution is due to the fact that this is the velocity of the light ray with respect to the origin of the system uppercase k, the origin of the system uppercase k, after the light ray is reflected. Let me repeat it. This is the velocity of the light ray with respect to the origin of uppercase k after the light ray is reflected. And notice that it can also be greater than c if v is greater than 0, and we assume v to be greater than 0, so this is greater than c, but this does not contradict special relativity, since it is a relative velocity, because it is a velocity of something, in this case a light ray, with respect to an origin. So it is not really a velocity of some point. Now, if we choose x prime to be small, we can rewrite this equation like this. It's easy to see. 1 over c minus v d tau dt plus d tau over dx prime. So you have to expand the equation above in a Taylor series, and you just truncate it to the first order. This is what you get. Here you get 1/2 1 over c minus v plus 1 over c plus v d tau dt, and this can be rewritten as d tau dx prime plus v over c squared minus v squared d tau dt equal to 0. It must be noted that instead of the origin of coordinates, we might have chosen any other point for the point of origin of the ray. And the equation we just obtained here is valid for all x prime, y, and z, because as I said, we can choose any initial point where the light ray can be emitted, and not just the origin. So this equation is quite general, actually. Now, for the propagation of a light ray along the axis eta, for example, because in this case we were considering the x-axis or xi-axis. So, if we consider the axis eta, which is parallel to y, now let's draw the y-axis. Here, for example, we have xi, which is parallel to x, and then somewhere here we have eta. They must be parallel, right? And if we emit a light ray from the origin, this light ray, for example, here, this light ray has a velocity equal to the speed of light c, and along the x-axis we are moving with the velocity v. So the motion of this light ray along this eta axis will be the square root of c squared minus v squared, just the Pythagorean theorem. It's the velocity when viewed from the stationary system. Since the points on the y-axis do not move along y, if we watch them from the moving system, it's easy to convince ourselves that we must have d tau dy equal to 0, according to very similar considerations that led us to this equation here. We can obtain this equation here, because in this case, as I said, it's easy to convince ourselves that the 2 points along the eta axis remain at the same distance. So this is the equation that you get. And similarly, we also get an equation of this kind, d tau dz equal to 0 if you consider the z axis and z axis. It is to be highlighted that tau must be linear on account of the properties of homogeneity which we attribute to space and time. From this, and this equation here that we found, we can write tau in this manner. It is equal to some constant with respect to the coordinates, but this can depend on the velocity v, and we will see that. And then this multiplies t minus v over c squared minus v squared times x prime. And if you insert this equation there, you can see that this differential equation is satisfied. Now, it is assumed here, in this expression, that at the origin of the system lowercase k, tau is equal to 0 when t is equal to 0. You can check that, because if we are at the origin of coordinates, we have x prime equal to 0 here, and therefore tau is equal to 0 when t is equal to 0. For a ray of light emitted at time tau equal to 0 in the direction of increasing xi, we have xi equal to c times tau. It's very easy to understand this, because the velocity of the light ray, c, times time, measured according to that frame of reference, gives us the coordinates along which the light ray is propagating. So we are assuming that the light ray is propagating along xi. And then, if we measure the time t according to the stationary frame, which is uppercase k, this is equal to x prime divided by c minus v, where, remember, this is the velocity of the ray with respect to the stationary system. Since the moving system is moving away from the stationary system, the velocity here should be c minus v. It's also quite intuitive. Then, if you put together these two expressions, and remember that tau can also be written like this, you can rewrite this in this fashion: xi equal to a of v times c squared divided by c squared minus v squared times x prime, and this can be rewritten in this fashion: a of v times c divided by the square root of c squared minus v squared times cx prime over the square root of c squared minus v squared. Now let's define this function here to be phi of v, because it simply depends on v and also the speed of light, but that's a constant, so it will depend on v. It's just the relabeling of the constant with respect to the coordinates, and this constant actually is a function of the velocity. So it is a constant with respect to the coordinates, as I said, but it is a function of velocity. And this can be written as phi of v, and then I will put beta here times x prime, where beta is simply 1 over the square root of 1 minus v squared over c squared. Like this. This is how Einstein defines these quantities. Then, analogously, if we consider rays moving along the other axis, we have eta equal to c times tau. So in this case, we are considering a light ray propagating along the eta axis. And in this case, we know that, of course, the coordinate x prime will be equal to 0, right? Because it's propagating along the eta axis. And then also we can write t equal to y divided by the velocity along the eta axis that we found earlier. This is the square root of c squared minus v squared. Simple as that. And from these equations, we can rewrite this as eta equal to a of v cy over the square root of c squared minus v squared. Now, if you remember the definition of phi, this is phi of v, This is equal to phi of V times Y. And very similarly, it's easy to find that zeta is equal to A of V times C times Z divided by the square root of C squared minus V squared. And this can be written as phi of V times Z. Now we know, remember that we know that x prime is equal to x minus vt, and we can rewrite the equations that we found. So tau is equal to phi of v times beta, and then here we have x minus vt, and remember this is xi, but then we have to divide this by c if we want to find tau. And also remember that for a light ray propagating along x or xi, we can also rewrite the equation as x equal to ct. So this can be written as phi of v beta times t minus v over c squared x. So in this case I have substituted for t this expression, x over c equal to t, so here we get v over c squared x, whereas here we can rewrite simply t, and this is one equation. Then we have the equation for xi, which is simply this one multiplied by c, so we can rewrite this as phi of v beta times x minus vt, like this, and then we have eta equal to phi of v times y, and we also have zeta equal to phi of v times z, like this. Now, at the time t equal to tau equal to 0, when the origin of coordinates is common to the two systems, let a spherical wave be emitted. Now, the points of this wave propagate with the velocity of light, c, and the equation of the wave according to the system x, y, z, t will be x squared plus y squared plus z squared equal to c squared t squared. It is easy to show that in the moving frame, the wave has the equation xi squared plus eta squared plus zeta squared equal to c squared tau squared. So in this case, it is also propagating with the speed c, the speed of light c, also in the moving frame. And it is very easy to do, it's just algebra. For example, you take this and you substitute the equations that we found above, and you will get that this equation will have to be satisfied. Now, if we want the transformations from xi, eta, zeta, tau to x, y, z, t, which are basically the inverse of these laws, the form of the equations will remain the same, actually. So, for example, t can be written as, we can write something very similar to this expression. We just have to change x to xi, t to tau, and also v to minus v, because we are looking at the frame in the other direction. So if xi is moving in this direction with respect to x with velocity v, it means that x is moving with respect to xi with velocity minus v. It is just the relativity principle. It is very easy to understand. And therefore we can write t as phi of minus v beta of minus v. So remember that also beta is a function of the velocity. You can easily see it from the expression beta equal to 1 over square root of 1 minus v squared over c squared, but this is also equal to beta of minus v if we define this to be beta of v. As you can see, because we have v squared, so if we change the sign of v to minus v, the function beta does not change. So we can also rewrite this as beta of plus v, doesn't matter. And then here we have tau plus v xi over c squared. And now if you simply substitute the expression for tau and xi that you find there, you can also rewrite this as phi of v times phi of minus v times t. So from here you can easily see that this product should be equal to 1. And also you get x equal to phi of minus v times beta of minus v or plus v is the same times xi plus v times tau. And if you do the algebra and you substitute the expressions for xi and tau, here you get something similar. Phi of v times phi of minus v times x. So also in this case, phi of v should be equal to the inverse of phi of minus v. Or basically, this product should be equal to 1. Then we get y equal to phi of minus v eta. And in this case, this is also equal to phi of v times phi of minus v times y. It's easy to see because from here, eta is equal to phi of v times y. So if you substitute it here, you get this expression. And also in this case, phi of v times phi of minus v should be equal to 1. And you get the idea. So you get also z equal to phi of minus v times 0, which is equal to phi of v times phi of minus v times z. Therefore, as I said, phi of v times phi of minus v is equal to 1. Now let's dig deeper into the meaning of phi of v. If we consider a rod along the eta axis whose endpoints are described by the coordinates xi equal to 0, eta equal to 0, zeta equal to 0 for one of the 2 points of the rod, and then the other point will be described by xi equal to 0, eta equal to L, and zeta equal to 0. According to the stationary frame uppercase K and the transformation laws, the endpoints will become like this. So if you simply substitute these values here, let me show you, if you substitute them here, these laws will become like this. You will get x1 equal to v times t, y1 equal to L over phi of v, and z1 equal to 0. This is very easy to check, as I said, because, for example, if you substitute these values here, you get t equal to phi of minus v beta of v times tau, and you also get x equal to phi of minus v beta of v times v tau, because you set xi equal to 0. And from these two, you can easily check that you get x equal to vt. Whereas from this law here, if you set eta equal to 0, you get y equal to 0, and similarly you get z equal to 0. And you also have to do something similar for these three values. So with these three values, you get the point x2 equal to vt, y2 equal to 0, and z2 equal to 0. From these 2 points, you get that the length of the rod measured in the system uppercase K is therefore L over phi of V. From reasons of symmetry, the length of the rod does not depend on the direction of the velocity V. Therefore, this should also be equal to L over phi of minus V, which implies that phi of v should be equal to phi of minus v. And remember that we also had the condition phi of v times phi of minus v equal to 1. And therefore, from these two equations, you get phi of v squared equal to 1. And you can convince yourself that the solution is phi of v equal to 1 plus 1, because in general the solution can also be minus 1. But if you choose the plus sign, the equations become tau equal to beta times t minus v over c squared x. And here you can easily check that when the speed of light is very large with respect to these velocities, this factor beta will be very close to 1, and this term here will be very close to 0. So you will get tau equal to t, which is coincident with Galileo's transformations, where time is absolute. This is also why you cannot choose the solution phi of v equal to minus 1, because otherwise you would get tau equal to minus t. And then you get xi equal to beta times x minus vt, and eta equal to y, and xi equal to z, where beta is equal to 1 over the square root of 1 minus v squared over c squared. And these were Einstein's considerations, which led him to find these laws, which are also known as Lorentz transformations.